Okay, in this chapter we're going to be looking at mass spectroscopy and infrared spectroscopy. While the chapter does talk about ultraviolet, we will not actually be using that or going into detail on that. Alright, so we're going to start with our first one, the mass, and then we're going to do infrared. And then first thing next semester, or next chapter, we will be on nuclear magnetic resonance, NMR. Okay. Now, mass spectroscopy is the first one we're looking at, and how that works is we're going to use a electron beam to bombard our sample. We'll be injecting our sample into like a vacuum chamber, and as it's being injected, you bombard it with an electron beam. The electrons are powerful enough; they'll just knock a single electron off the molecule, creating the molecular ion, which is this M+. Reason this comes in handy, that M+, that radical cation, will be attracted or affected by magnetic fields. So we actually will run it through a magnet, a very fixed magnet, and let that deflect those masses, that mass sum. So since it's now got a charge to it, it's going to actually be affected by that magnetic field, and we're going to get separation. Now it's showing multiples. Technically that molecular ion, that M+, is that one on the end, or it's the one that's deflected as little as possible. What these other are is, turns out that that molecular ion, being a cation, is not very stable, and it will fall apart, it'll fragment. Now, if I were to look at pentane and actually run it through this is the type of fragmentation patterns I see. Now, this is a very typical fragmentation pattern where I see for any alkane. That loss of 15 is a very common thing, and then a loss of 29 is a common thing. And really what that is, 15, that's a CH3, and M29 is a CH3, CH2, which is why alkanes typically have very predictable behavior, because they're breaking off carbons and hydrogens. Alright, but let's talk about that molecular ion a little bit, and actually talk about what happened to it to create these little peaks. Because this isn't a peak made up of CH3, that's the loss of CH3. So what happens is, to create that peak, that's this third one down here, this is where that 57 was created. That molecular ion, being a little bit unstable, fragmented, and it created a radical and a cation. Now it could have been the cation is on the small particle and then created the radical here, and if I back up we can see there is an actual positive 15 one. Hang on, my screen froze. There we go. And there is our methyl cation. This down here was basically the 4 carbons. And let's see, this would have been 1, 2, 3, 4, 5, 6, 7, 8, 9 hydrogens positive. Now the other 2 peaks that are actually more abundant are just those next 2 above it, so a 29 and a 43. Now that should make a little bit more sense why those 2 would be more populated than this. Technically, that methyl cation or that methyl radical aren't very stable for the same reasons they weren't stable in the last couple chapters. That's why they're such small peaks. Both of these are very hard. These reactions don't happen super easy because they create those methyl radicals or methyl cations. These secondaries are a little bit more stable, which is why they happen more often. Now, 43, this crazy peak, does actually do some weird thing, which actually is why this pattern looks so much more broad. Remember how our cations can rearrange? Well, that 43 rearranges in the stream. And what it actually ends up doing is it kicks a couple of hydrogens off as radicals and creates more like an allylic cation. Happens very common. Anytime you have a 43 ion form that has the cation on the end, it will rearrange like that a little bit more easily. Alright, so let's look at something else. I have 2 different chemical structures that are C5H12. But if I look at the fragmentation pattern, I see something drastically different. Both have that parent of 72, but my M-15, which is very small like the last one, is really huge over here. All right, so what about that structure makes it happen a little bit easier? Well, yeah, if you think about it, if we rip this off as the radical and make that the cation, that's a secondary cation, something we know is far more stable. And sure enough, that's exactly what happens. That kicks off, creates that cation, much more abundance and presence just because of that secondary effect. Now the 15's not increased, because if I were to rip this off, while that does make a better radical, it's still not a good cation. That's still a CH3. That doesn't make the CH3 any better than it was before. So we don't see a significant increase on the 15. Alright, so we can do a few things from this that is going to pay off tremendously. Now, the big thing, rather than try to explain those fragmentations yet, we're going to try to see if we can identify what the parent ion is, or more importantly, what the molecular formula is. Or in mass spec, that's what that radical parent cation is. Now, we're going to do something weird with that number. It will always be a nice, even, whole number. You're going to start by dividing that number by 13. Now, we're using that 13 to represent the carbons. And while we're not using 12, the reason we're not is because it's almost always going to have at least one hydrogen, or at least on average. So that 13 is going to give us a little bit more of a ballpark starting number. So if I were looking at something that has 142 for the mass number, and I wanted to actually figure out what it is, I would start by just dividing it by 13 and taking the next, the whole number, drop the remainder. And I get a C10 out of that. Now that would be 10 carbons would be 120, so if I just do a subtraction, that tells me how many hydrogens there are. And if I look at my elements of unsaturation, that's a saturated hydrocarbon. That is just C10H22, that is decane. Now, we don't know anything about how it's put together, but we do know what the molecular formula is from just that parent ion. Now, there might be times where we're told there's an oxygen in there. Well, if there is, we're just going to subtract that off before we do any math. We'll still divide by 13 after we've done that subtraction. This time we get a 9. That's going to give us our carbons and our oxygens, and then we still just do the same thing. Just do a little bit of math, figure out how many hydrogens there are, and then figure out how many elements of unsaturation the molecule would have. Alright, we can do something like that for nitrogen, but we have a benefit. Turns out, if there is nitrogen present, the parent ion, or the molecular ion, will end in an odd number. About the only time you're going to see it end in an odd number is if there is an odd number of nitrogens present. So, what I would do if I had a mass of 71, let's assume it has just one nitrogen in there. I subtract that nitrogen, divide by 13, and I'd have 4 carbons. So C4N1H9 does work. If I thought it had 3 nitrogens, I'd do the same thing and I could get a formula for it. Now the reason I didn't do if there was 2 nitrogens is because if there were an even number of hydrogens, the parent ion would go back to being even. Now, as you can tell, I'm not talking about how we could tell the difference between C4N1 or C2N3. And that's really because at this point we can't tell them apart. We're going to need a little bit more. Now, regardless, on this case, both of these do imply the same thing. They both would be, one would be single bonds, one of them would be 2 elements of unsaturation. That might help us identify them based on that. But that's some of the other clues we're going to have to look at it. Alright, so let's add to our degrees of unsaturation. We talked about this back several chapters ago. If you want to calculate it, you take the number of carbons, multiply it by 2, and add 2. Then you subtract the number of hydrogens, and you divide that by 2. Well, we need to add carbons we need to add to our carbons and hydrogens. We need to add oxygens and nitrogens, and then all of our halogens. And the formula just ever so slightly changes. What we're going to do is still take the number of carbons and add 2. But we're also going to add the number of nitrogens. And I'm going to put 1 times the number of nitrogens. We're not doing any math, anything doubling of that. It's just the number of nitrogens. And we're going to ignore the oxygens. We're going to subtract the number of hydrogens. I don't know why I put 14 there. That's supposed to be like number sign. Subtract the number of hydrogens and the number of halogens. And then still divide it by 2. Now the reason we did the difference on the nitrogens, if you think about a straight chain of carbons. I'm going to just leave a little dash right here. The 2, for the 2 on the carbons, were the 2. And then the 2 ends were the 2 ends. Well, if I add a nitrogen to that, going out one more further, that's still the end. The only thing I have to add to it is the 1 hydrogen that would be there, because this other side is a lone pair. So that's why it's just 1 times the number of nitrogens for the number of spots off of it. And oxygens, we totally ignored it because both sides of the oxygen are lone pairs. Alright, so we've modified our degrees of unsaturation, but we see that it is doing the same type of thing, and it still means the same thing. It just tells you the number of double bonds, or the number of pi bonds, or the number of rings. Alright, so let's take it a little bit further on here. Let's say we figured this out and it's nothing but carbons and hydrogens, and we believe it's a ring. Has a molecular ion of 98 and has a base peak of 83. Alright, so I'm going to start by dividing that by 13. Excuse me. And if I do that, I end up with 7. And, excuse me, if I take that 7, multiply it by 12, and then subtract that by, take that 7, multiply it by 12, I end up with 84. 84 minus 98 would give me my number of hydrogens. So I end up with a formula of C7H14, which does support my 1 element of saturation being the cycloalkane. Alright, so this implies a ring, and my base at 83 tells me something important. The difference there being just 15, it does tell me this thing loses a methyl radical relatively easily. So it kind of tells me it's leaving something secondary behind. That strongly implies a ring with a single methyl off of it. Alright, let's do another one of these. I'm going to skip this right there. So 98 with the base is now at 69. Still a cycloalkane, and we still have that exact same formula, C7H14, because the mass was 98. But now our main loss is 29. Well, that implies a 5-bonded ring with an ethyl coming off of it. Alright, now we can actually utilize the book and figure out that fragmentation patterns that pop up. We're going to spend a little bit more time trying to look at what the parent ion is. We're going to try to figure out the structure based totally on that. Alright, so we're going to look at just that parent primarily. At least that's our primary thing we want to get something out of. Now, when we were talking about that, we were using that molecular ion to get the molecular weight, and we were ignoring that little peak off to the right. If you back up all the mass specs that you've seen on this lecture and all the ones in the book prior to this have that one little peak there, and we've ignored it. The reason we're ignoring it, turns out it's roughly 1% of this. And the reason I know it's roughly 1% is because most carbons are carbon 12s. That makes about 99% of the natural abundance. Carbon 13s make up about 1%. We are actually seeing that abundance, that natural abundance there. That ever so slight amount of difference is what creates that smaller thing. Well, Question is, can we take that to advantage to actually identify other parents? Turns out we can, because often we have abundance ratios that are different. Like for instance, where that carbon and carbon pay off pretty much, we don't see that with hydrogen, and we don't really see that with nitrogen. The number is too low. Fortunately, nitrogen is going to be an odd number for us, so that's going to help us out even more so. Oxygen probably won't show this. It's typically just too small. The reason I say probably, it turns out it's easy enough to actually manufacture that and add it to a sample that you might end up using O18 to help identify something. But for the most part, if it's a natural containing substance, the oxygen is just adding that 16 to it. Now, the sulfur pretty much does show a noticeable M+2. So if you notice it, it probably is sulfur, because chlorine and bromine, which have it, are much more noticeable. This is about 3 to 1. Here's about 50-50. And what I mean by that 50-50 pattern are those fragmentation patterns. You really do see that in the parent. It's like chlorine, we do see an M and an M+2. And we are seeing about a 3 to 1 ratio. Pretty much always. The only time we really see that is with chlorine present in that parent. As a matter of fact, when we see it in the little fragmentations, we know that that fragment, whatever it is, has chlorine in it. And if I were to look at bromine, I see the same type of thing, except now the parents are equal, because it's a 50-50 ratio. Now, if I back up to my isotopes, see the iodine really only shows one isotope. Fortunately, it is easy to tell if it's present. Going to have a huge difference between that and typically the most abundant isotope. Going to be difference right at 127, the mass of iodine. A nice giveaway. All right, now, we did see on there that oxygen has that small M+2, and it'd be nice if it shows up. Fortunately, we have a couple other things that pay off tremendously for oxygen-containing species. First, for the most part, we will be able to tell if it's an alcohol from other chemical means, and the mass spec almost never shows the OH, the full molecular ion. Basically, what happens is we denature that. It comes off so easily, and it leaves as water to help stabilize the molecule, that the parent is pretty much never present for an alcohol. The parent is almost always M-18, which is what that is right there. And what really happens is, and the way to stop it, are alcohol and a carbon, 2 carbons away, that has a hydrogen on it. Those two leave, and that radical cation gets split out. So it's a radical cation in 2 separate locations. Happens often on alcohols. All right. Last little thing that we're going to talk about here. Your book spends a lot of the time talking about how the fragmentations can help predict these peaks. Like, for instance, we could take that 116 and some of this other stuff and figure out the exact molecular formula here. And we would end up with C7 and O, and then what's going to be 14 hydrogens? No, 16 hydrogens. But to actually get it put together the way it's shown there, you would actually need to solve how this fragmentation and how the molecule is coming apart. And that is doable, and our book gets you on the right start. But we're actually not going to do that in class. In class and on the test, we're focusing on identifying what the parent tells us. Just getting that molecular formula from what the parent is. Where that fragmentation pattern will come in handy, we're going to look at some of this stuff in lab in Orgo 2, and we're going to do some more detailed studies of mass spec and how it fragments. Alright, last neat little thing about mass spec. Now, all of our mass spectra that we saw here actually show mass to charge just a nice whole number. Well, if we actually had better equipment or a reasonably good mass spectrometer, you can get a lot more digits off there. You typically can ignore it with organic chem. The reason we're not necessarily always going to, turns out these three things down here all have a mass of charge right around 86. Well, a mass spec that's a high resolution mass spec can tell them apart simply because the significant figures get to be more important when we start combining the exact masses of those common isotopes. And using those exact masses, we can get the exact molecular formula from that mass to charge ratio. So high resolution does pay off on some of that stuff. Okay, next little thing we're going to look at, and we're going to do a lot more with this, and even bring some of this into the organic lab and organic too. We're looking at a different type of spectroscopy, looking at the infrared spectroscopy. Now, there is visible spectroscopy, and there is ultraviolet, and they both have uses. Organic does actually have a lot of benefit of studying the ultraviolet frequencies. Visible, not so much. Most of ours are colorless liquids, and they don't really do much in the visible spectra. But infrared, they stick out. They glow. They're very useful in identifying what functional groups are present just by looking at the infrared spectra. All right, so let's expand that infrared spectra. What we're going to see is, we're going to see that the molecules are vibrating in the wavelengths that make up the infrared spectra. Now, what I mean by frequencies and vibrations, I got a little video here I was going to bring up. This is what the molecule is doing all throughout there. There's various different vibrations going on. You got some symmetric, you got some vibration, you got some bending, and it even happens on the entire molecule. So the entire molecule will be affected by one little thing twisting. See how this little bond is just rotating? It's twisting. Well, it's causing the whole molecule to actually do little vibrations. We can model that some, but that's not as beneficial.
In this online lecture, we're going to discuss the basics of IR.
Didn't want that to start talking. That's okay. We actually are going to take advantage of that result of those vibrations. Like, for instance, a carbon-oxygen double bond happens to absorb energy right around 1700 wave numbers. OH is right around 3300. And all carbonyls do in all OHs. We could almost think of those as maybe colors, like on a color wheel, and they're going to blend together, but all alcohols would actually absorb right around there, and anything with a carbonyl is going to be right around there. All right, well, so what does that translate to? When we actually look at the entire spectra of a molecule, we see certain peaks that tell us a lot about how the molecule is put together. For instance, this nice little broad peak down here, that is definitely an OH in that molecule, and being broad is a very distinguishing characteristic of that OH. Even this much more narrow, we're going to find that this is broad for this region. Never as broad as, but is broad. That's a good example of a carbonyl. All right. Problem is, turns out the rest of this is not told about in that structure. What I mean by that, we're going to see that this peak, that carbonyl peak, and that hydroxide peak, that OH peak, would happen in almost any molecule that has those two functional groups. They show up in very distinguishing locations. We actually see them all in this range, 4,000, 1,500 wave numbers. But they always show up in the exact same location. So they actually identify the functional group, not necessarily the molecule. The fingerprint range, or everything else, actually distinguishes the individual molecule. What I mean by that? Let's look at pentanol. Now, reason I just said pentanol like that is because there is 2 pentanol and there is 3 pentanol. But I want you to look at these main peaks. I have this OH peak here, I have this OH peak here. These are just carbons and hydrogens. on this lower end here, they both look almost identical. Where their distinction happens to be is in this area we call the fingerprint range. Now both of these things, these other peaks down at this right end, they do talk about those individual bends and flexes and whatnot, but we never try to identify what those peaks and stretches are. What we're going to see the IR tells us is both of these told us the same thing. You had an alcohol. There was nothing about these particular IR spectra that told us it had 5 carbons in it. There was nothing that told us it was a 2 or a 3. What we could have done in the real world is had a bunch of alcohols in, say, like a database, and then we can match it up to these fingerprints. Just like, think about fingerprints for like crime scene investigation. You're checking if somebody stole something, you're looking for their fingerprints. We really do the same type of thing with molecules. We look for their fingerprints to guarantee it. What we're going to see is we're mostly going to use IR to identify what functional group is present. Alright, the reason that happens is because they do show up in totally different areas. When the bond is more polar or less polar, the polarity of the bond actually makes the peaks much more intense or non-intense. CH bonds are typically not very noticeable because they're not really polar bonds. That's why these cluster here that looks like just a bunch of single peaks overlapping, those were all these individual CH peaks just overlapping with themselves. And that's why it does look broad, but if you look at the top, it is individual little peaks. They're just overlapping. Very common thing that you see with CHs. But OHs get to be a little bit more intense just because they're that polarity. We also see that the type of bond shows up where it's located. Carbonyls show up different locations than carbon-carbon double bonds. So there's a lot of differences. Now, rather than try to talk about why they show up at different locations, let's just look at a chart that actually shows where they show up. Now, we could actually memorize this entire thing and actually utilize this, and I do need you to actually get kind of comfortable with it, but we're going to see there's more to this category, because there's a lot of functional groups that have carbonyls in there, and this is a pretty big range. We can narrow it down some because certain things happen. Alright, so instead of looking at numbers, what we want to focus on is 3 areas on your spectra that we need to identify everything in. Alright, so we got the 2 green areas, and we have the blue area. Now, we're not necessarily going to say we need to start with one area, one of those over the others. I am in the lecture notes, I'm going to go over one area. But any peak you find in any one of those 3 areas, you want to identify and figure out what it is. And the entire molecule needs to actually be identified based on all those peaks. Alright, let's look at an example of what I'm talking about. We're going to focus on those double bonds. Now, the double bond region, that is this section down here. That's where all your double bonds show up. Now, if we look at the that numerical breakdown, carbon-carbon, carbon-nitrogen, and carbon-oxygen, they're all in that range, roughly 1600 to 1800. But turns out they are very distinguishable for the most part. All right, what I mean by that, let's look at the carbonyl, so the carbon double bonded to oxygens first. Alright, reason I'm picking on those is because being further apart in the periodic table, that bond is a lot more polar. It's typically going to be more intense than the other two, so going to be much more measurable peak, it's going to be much more obvious. Alright, something else that factors into it. We have different functional groups that have carbonyls in it. That's never identified as a functional group, it's what else it's attached to. The other thing that attaches to it creates a different vibration here, affects that double bond, and it causes it to move. And esters, for instance, actually put that carbonyl up about as high as it goes. It's going to be about at 1740. That's about as high as you will see it in normal situations. And it's going to be that nice and broad for a double bond peak. And the other weird thing is we will see a CO bond. There is going to be a noticeable peak in this area, in the fingerprint range, somewhere between 1300 and 1100. It needs to be there. It often disappears in the noise of all the other vibrations, but as long as you have a peak in that range that's at least somewhat intense or nearly as intense as the carbonyl, it's a good indication you have an ester. But really, as long as you see that 1740 thereabouts and it's nice and broad like they're showing, that's about the only thing that it could be, with the exception of an aldehyde. Aldehydes can be close to that, but they can be as low as 1720 as well. Fortunately, though, an aldehyde going to have something else that gives that definitely tells the difference. Turns out that CH is not going to show up with all the other CHs like we were talking about and be clustered together. Because it's near this carbonyl, this CH vibrates differently, and it creates these two secondary peaks. And these are by far the best thing about aldehydes. The only reason you're ever going to see a peak around 2700 or 2800, and you will always see both of them, is if you have an aldehyde present. So, dead giveaway. If I have that nice broad CO peak, just like an ester, but I have that 2800 and 2700, I have an aldehyde. It's the only thing that does that. Alright. Let's take away that H, put the carbonyl between two carbons, and make a ketone. Alright, that takes away anything special. The CHs stay exactly where they are. The carbonyl stays relatively broad and intense, but it drops it down to about 1720 or so. There's your big difference. It's actually lower in energy, and there's nothing else that really tells us that there's something special attached to that carbonyl. Alright, we have two more carbonyl functional groups, and if you've noticed, I've been going lower in wave number, and my next one, which is the carboxylic acid, is even lower still. It's going to be almost as low as 1700 in some cases. It's typically, though, broader and more intense. The biggest reason that is because this OH that's in there, so carboxylic acid, this OH causes a big, huge change in the stabilization. And we see this OH broad peak pop up here. But this is a huge broad peak. It's going to be centered around 3000, and it's going to cover up an entirely huge area. Biggest reason it is this broad, when molecules with hydroxides, carboxylic acids, or alcohols get in there, hydrogen bonding interferes or adds to those vibrations. It changes how much those vibrations actually interact, so we don't get these narrow peaks, you get much more broad peaks. But there won't be really a spike. The reason this one has a spike is because the CHs are being overlapped. Typically an OH peak is just a very nice hump. Just so happens that this particular hump is centered around the 3000 peak that represents our CHs. Alright, last functional group, very low frequency, it's the amides. This is about the only time you're going to see a broad peak for that carbonyl under 1700. This can be right around 1650 on average, but it's still going to be broad like that. The other plus that you have here is you may get these weird peaks, kind of like our carboxylic acid did, but they're going to have fine peaks to them. It's going to still be a very broad thing, but there might be some noticeable peaks. The reason this one has two peaks is because this particular one has two hydrogens attached to that amide. If we'd only had one H, and if this other thing was just maybe another methyl, then we would only have one peak at this end. Alright, now that's going to break down our carbonyls and get that distinction going on. Now, before I start talking about the other double bonds, the carbon-carbon double bond, I'm going to talk about the single bonds area, so the other green area. So this was the farthest one down, and we already talked about seeing OHs and NHs, and that's what we're going to complete here and point out what we're going to see that's different on alcohols than carboxylic acids. Alright, so we saw this before. This was the very similar to the spectra we saw for pentanol. This is butanol. Typically an OH peak is a very noticeable broad peak. It's going to be centered right around 3300. The only reason it was at 3,000 on the previous one we saw was because that was part of a carboxylic acid. OH peaks are always nice bell curve type things. Amines will be still broad, not nearly as intense because we're not nearly as polar, but they will almost always have a slight spike to them. And it'll have more than one spike if there is more than one NH. So this particular amine only has a single H on there. Had we changed this to somehow have two hydrogens and then all those other carbons on there, you would see two peaks down here. So the number of peaks typically tell you the number of hydrogens attached to the nitrogen. Alright, now, all these others we've been it's been in all the others. Those are just CHs. And the reason we ignore them is because if it's an organic molecule, it's likely to have a CH bond. So you're going to see that peak in that 3,000 range. A lot of those little noisy peaks. Well, it turns out our other double bond will actually be somewhat useful in looking for those other carbon hydrogens. So what I mean by that, if I look at an alkane versus an alkene, nothing but carbons and hydrogens with single bonds, nothing but carbons and hydrogens, but at least one double bond, I see something different pop up. First thing to notice, in my CH area, I have a small little peak all by itself, but it's higher than 3,000. And I also have a very narrow peak around 1650. Now, those two things are dead giveaways you have an alkene. Double bond around 1650, a CH bond that is slightly higher than 3,000. You'll still be narrow, and this will still be narrow, but they are different. They're definitely going to be different than a OH or an NH bond. This is going to be definitely different than a carbonyl. Weird thing is, on an alkene though, it might not be there. Remember how we said the intensity was based on polarity? Well, the reason these are polar is because this molecule is actually somewhat polar. It's not polar by a lot, but it's slightly polar. But if I take those 6 carbons from that one hexene and move them around, if I put the 4 methyls off of the double bond, this CH peak would go away because there is no H coming off that double bond. And because the left and right side of this molecule are identical, that molecule is non-polar. The spectra for this looks like this one. The double bond and that CH for the sp2 carbon are hidden. Alright, so sometimes we identify that carbon-carbon double bond from lack of information. You might not see it. But you would typically know your molecular formula, so you would know if it had an element of unsaturation. You typically, though, if that's the case, you have to build your molecule based on the nonpolar nature of that. Alright, last little area, the triple bond area. Now, saving this to last because we're going to see the same type of thing with alkynes as we did with alkenes. When we see that narrow peak that represents the triple bond, so it's just going to be under, or a smaller number than 2200, so less than 2200. That's going to be a carbon-carbon triple. And if you're seeing it, you're probably also going to see this thing down here, which is a narrow peak but shifted around 3300. That is this H. What you're seeing is a terminal alkyne. Because alkynes, as soon as I move them into the middle of a molecule or make it symmetrical, that carbon-carbon triple bond totally disappears because it's no longer polar enough to be noticeable, and there would be no CH to show up here. So alkynes, like alkenes, can disappear on infrared spectroscopy. So look at the elements of unsaturation. If you can't explain pi bonds, it's probably something like this. It's an alkene or an alkyne. Because the other source of triple bonds, nitriles, they're not going to hide at all. A lot more polar because the difference, and these are going to show up slightly higher than 2200 and always going to be more noticeable. All right, that gets us done with this. I know we're going to get a chance to actually apply both these techniques in lab in organic too, and we're going to bring in NMR in the next chapter actually and complete the whole picture of our instrumentation. All right, thank you.